Hi friends, welcome back to our series of sessions on control systems simplified. Today we'll be discussing on modeling of mechanical control systems. We'll be discussing the differential equation modeling of mechanical systems, which are of two types based on the type of motion. We call them as translational mechanical systems, rotational mechanical systems. Translational mechanical systems move along a straight line. These systems mainly consist of three basic elements, which are nothing but mass, spring, and dashpot. We also call damper to the dashpot. If a force is applied to a translational mechanical system, then it is opposed by opposing forces due to mass, electricity, and friction of the system. Since the applied force and the opposing forces are in opposite directions, the algebraic sum of the forces acting on the system is zero. That's why let's see how these forces opposed by three individual elements, mass, spring, and dashpot. Let's understand them. Mass is the property of a body which stores kinetic energy. If a force is applied on a body having mass m, then, which we can see it from the figure, then it is opposed by an opposing force due to mass. The opposing force is proportional to the acceleration of the body. Assuming elasticity and friction are negligible, we get F of m because of the mass, force because of the mass is proportional to A, and F is equal to ma, which we know it in the intermediate itself, where A is nothing but the acceleration, d square x by dt square. So F is nothing but m into d square x by dt square. So that's the differential equation for the mass system, where F is the applied force, Fm is the opposing force due to mass, and capital M is the mass, A is the acceleration, x is the displacement. And acceleration is always the second derivative of the displacement. And if you see, the spring is an element which stores potential energy. If a force applied to the spring K, then it is opposed by an opposing force due to elasticity of the spring. This opposing force is proportional to the displacement of the spring. Assuming mass and friction are negligible, we get force is proportional to x, again displacement. So F of k, because elasticity constant, spring constant, is equal to kx. K is the spring constant. So finally we get F equal to F of k equal to kx, where F is the applied force as usual, and F of k is the opposing force due to elasticity of the spring. K is the spring constant, x is the displacement. Similarly, we have the dashpot. If a force is applied on a dashpot B, then it is opposed by an opposing force due to friction of the dashpot. This opposing force is proportional to the velocity of the body. As usual, assuming mass and elasticity are negligible, we get F of B is proportional to V, and which is nothing but BV, where B is nothing but the frictional coefficient of the dashpot. So V is nothing but the first derivative of displacement, B dx by dt. So we get V is velocity, and F is equal to Fb is equal to B into dx by dt. So these three are the individual elements of the translational mechanical systems. Now let's see the modeling of rotational mechanical systems which move about a fixed axis. These systems mainly consist of three basic elements. Those elements are moment of inertia, torsional spring, and dashpot. If a torque is applied to a rotational mechanical system, then it is opposed by opposing torques due to moment of inertia, elasticity, and friction of the system. Since the applied torque and the opposing torques are in opposite direction, the algebraic sum of torques acting on a system is always zero. Now let's see these systems individually. The first one is the moment of inertia. In translational mechanical system, the mass stores kinetic energy. Similarly, in rotational mechanical system, moment of inertia stores the kinetic energy. If a torque is applied on a body having moment of inertia J, then it is opposed by an opposing torque due to moment of inertia. This opposing torque is proportional to angular acceleration of the body. Assuming as usual elasticity and friction are negligible, we get Taj. J is nothing but because of the moment of inertia, is proportional to alpha, where alpha is the angular acceleration and theta is the angular displacement. T is the applied force. Tj is the opposing torque due to moment of inertia, and J is the moment of inertia. So the resultant we get J alpha and J into d square theta by dt square. As usual, the angular acceleration is the second derivative of angular displacement. Next one is the torsional spring. In translational mechanical system, we have seen spring stores potential energy. In this rotational mechanical system, torsional spring stores the potential energy. If a torque is applied on a torsional spring of K, then it is opposed by an opposing torque due to the elasticity of the torsional spring. This opposing force is proportional to the angular displacement of the torsional spring. Assuming, as usual, the moment of inertia and friction are negligible, we get Tk is proportional to theta, where T is the applied torque here, and Tk is the opposing torque due to the elasticity of the torsional spring. K is the torsional spring constant and theta is the angular displacement. So ultimately we get T equal to T of K equal to K theta, where K is the spring constant. Next we have the dashpot. Similarly, if a torque is applied to a dashpot B, then it is opposed by an opposing torque due to the rotational friction. Earlier it was translational friction of the dashpot. This opposing torque is proportional to the angular velocity of the body. Again, moment of inertia and elasticity are negligibly assumed. So T of B gives proportional to omega, where omega is the angular velocity, theta is the angular displacement, B is the rotational frictional coefficient of the dashpot, and TB is the opposing torque due to the rotational friction of the dashpot. So ultimately we get T that is equal to opposing TB, that is nothing but B into d theta by dt. So these are all the mechanical modeling of the mechanical systems that we come across in the control systems. So that's all for today, and let's meet in some other topic of the control systems simplified. Thank you very much.